All right, welcome back, everybody. This is part 2 of our Existence and Uniqueness Theorem series. Last time we talked about the linear existence and uniqueness theorem. That's this guy at the top of the page. Oh, there we go. Off to a great start. There we go. This theorem at the top of the page deals with linear first-order equations. And what we did we didn't show that this theorem was true. We just showed how to use it. And we had an example down here showing how this theorem essentially guarantees not only a unique solution to an initial value problem, but it tells you exactly the solution space, right? The interval, the maximal interval over which this solution is defined. So this is where we make the distinction between the linear and nonlinear equations. It's because linear equations have the ability to do that. Nonlinear equations do not have such an ability, right? And this is where we bring in our, wow, what is that shape? That is a star. There we go. We bring in the heavy hitters now. This is the existence and uniqueness theorem for first order equations, right? This is a very important result. And the key thing about this result is that we don't have to solve the differential equation in order to know that there is a solution to it. In fact, that there is a unique solution to it. Right, and this is a little bit different from how you would prove this in the linear case. Oftentimes, an existence proof can be as simple as just creating a solution, like coming up with a technique that solves a broad category of differential equations or broad collection. This theorem down here, I'll start again. It's that important. This theorem. There is no general solution technique for a first-order differential equation, right? Even the simplest differential equations oftentimes don't have explicit solutions. Therefore, we need to know when a solution exists, even in the cases where there is no known solution technique, no explicit solution for this equation. So in this case, let me go ahead and kind of outline what this theorem is saying. Now, we are looking at dy dt equals a function, rate function of t and y, and we have f of t0, an arbitrary initial condition equal to y0. And we would like to make two assumptions, and they're specifically about this rate function. One, that f is continuous, and partial f, partial y is continuous, right? So this is the first partial derivative of f with respect to y. So effectively, you take your differential equation, you take your rate function, and you differentiate that guy with respect to y while holding t constant. And we'll do an example downstairs in a moment. But these two guys have to be continuous over and we'll say this is an open rectangle that contains our initial condition, so containing t0 by y0. Okay, so if we are doing this in the plane, we've got t on the horizontal, y on the vertical, and the idea here would be to put our initial condition out here, and I'll do this guy in red. So there's t0, comma, y0. So that's my initial condition, and what I would like to guarantee is that there is some open interval around t, around t0, and some open interval around y0 or y0. And this rectangle needs to guarantee that both of these functions, f and partial y, are continuous in that rectangle. Okay, so if I can do that, if I can guarantee that our rate function is what's called a C1 function on this open rectangle that contains my initial condition, then I know that there is some interval in here, and I'm going to do this in white to make it stand out. Then there is going to be some interval around t0 that guarantees that my solution exists over this interval. And this is the t0 minus h and t0 plus h that's mentioned in this theorem. Before then, we had alpha and beta as being the left and right endpoints of the rectangle, and oh, come on, go to green. There we go. And then we had gamma and delta as being the bottom and top endpoints of this rectangle. So this is the idea that even though I'm able to show that my function is continuous on both the, it's a C1 function, it's continuous and has a continuous first partial derivative in y, then I can guarantee that there is at least some sub-interval here, right? I'm not necessarily allowed to take the entire rectangle here, but I know that there is going to be some interval about t0 where my solution exists. And in fact, it will be unique there. So this theorem statement is remarkably subtle, and I'd like to show you a little bit more about how we would use this in practice. So let's go ahead and do an example. So I'm going to go ahead and take dy dx equal to this rate function, 3x squared plus 4x plus 2 over twice y minus 1. You might recognize that we did an example like this in an earlier video. Just check out the playlist for separable equations. And what we wind up saying here is that we would like to make this into a linear equation, but as it stands, it is not linear, because if I were to expand this out a little bit, I'll wind up with y prime and a y minus 1, and I'll have 1/2 3x squared plus 4x plus 2. So the fact that I have a y prime times a y term means that this is a nonlinear differential equation. Okay, so that means I can't use theorem 2.1. I can't figure out an entire, like a maximal solution domain here, but I can use theorem 2.2, the nonlinear existence and uniqueness theorem, in order to show that there exists a solution. So let me go ahead and identify the parts that we need. This is going to be my rate function. Right, so this is my f. So f of, and in this case, the independent variable is x, not t. So f of x and y is going to be this ratio 3x squared plus 4x plus 2 over twice y minus 1. And my initial condition will be t0 by y0 equals 0 by minus 1. Great. Now, I need to make sure that this is a continuous function at that location, right, at this initial condition. And the only places where this is discontinuous for y equal to 0. So any point in the plane where y is equal to 1 is what's going to wind up giving this, giving part of this rectangle. Let's see. We could also check out partial f, partial y. And this is where I said, remember, we're treating the x, or the independent variable, as a constant here. So it's 1/2, that'll be 3x squared plus 4x plus 2, times the derivative of 1 over y minus 1, right? I'm treating every other bit of this expression as a constant. And I can go ahead and differentiate 1 over y minus 1. That's a power rule, no problem. 3x squared plus 4x plus 2 times minus 1 over y minus 1 squared. Okay, and we ask, where is this guy continuous? And it's going to be for the same locations, right? So that means that my box here, the thing that I created upstairs, let's see, my initial condition is at 0 by minus 1, so I should have moved this guy way up here. There we go. So y, t, 0 by minus 1 puts my initial condition roughly here. So this is 0 by minus 1. And I know that my solutions, or my rate function, is discontinuous for y equals 1. So that means that, and I also check my first partial derivative with respect to y, and that's discontinuous at the same location. So that means there's no restriction in the x, and there is but the one restriction in the y. So that means that I know that my interval can extend from minus infinity to infinity in t. So t can be anywhere in this interval. And y, let's see, that would be gamma would be the lower bound. So this extends all the way down to minus infinity, but it does stop up here at 1. Okay, so this is the box. This is my rectangle where I'm guaranteeing that my rate function and its first partial derivative with respect to y are both continuous, which means that I have a solution somewhere on the real line, right? There's some neighborhood of this location that I can guarantee a solution. And we did actually find this solution. Well, if I remember that this is an x and not a t. There we go. So I can recall from our earlier example that we solved this explicitly. Y equals 1 plus or minus the square root of x cubed plus 2x squared plus 2x. Right? That was our particular solution to this original initial value problem up here. So what I wind up with is just a theorem that tells me that I get exactly one solution here. And I can tell you which one I get by, let's see, what would it be? I'd have to plug in a specific value. Oh, I guess I wound up doing this backwards in my notes. Shame on me. We can actually figure this out. So this solution over here is not quite right because I used a different y and t value. But anyway, let's actually figure this out. We can do it real quick. So let's make our solution. Right, we're in the rare instance where we can create the solution. So separate variables. This will be dy, and then I'll get twice y minus 1, and that was 3x squared plus 4x plus 2, integrating dx. Recall, and then there we go, y squared minus twice y is equal to, that'd be an x cubed plus a 2x squared plus a 2x plus a c. And if I use my initial condition, y of 0 equals minus 1, that would be 1 minus a negative 2, which is equal to a c. So c is actually equal to 3. Excellent. So that would mean that I get y squared minus 2y equals x cubed plus 2x squared plus 2x plus 3. And I can solve this with a quadratic formula if I move everything over to the other side and treat the x pieces as constant. So this would be plus negative x cubed minus 2x squared minus 2x minus 3 is equal to a 0. So y equals would be 2 plus or minus the square root of 4 minus 4ac, so plus 4x cubed plus, you know what, that's plus, I can actually factor this bit out. So that'd be a 2, so that would be, oh, I did it a little fast. That'd be 1 plus x cubed plus 2x squared plus 2x plus 3. There we go. All divided by 2, so there it is, 1 plus or minus the square root 1. I can pull that out. So x cubed plus 2x squared plus 2x plus 4. And to get the correct initial condition, all right, I have to identify which one of these plus or minus branches I'm sitting on, and that would be based on my initial condition. If I plug in y equal or x equals 0 here, then y of 0 would be 1 plus or minus the square root of 2. So it's, oh, sorry, square root of 4, which is 2. So it's either 3 or minus 1. So this is the positive branch, and this will be the negative branch. So I need to take this guy. So that means my solution, coming full circle here, it's going to have to be 1 minus x cubed plus 2x squared plus 2x plus 4. And I think we can tell that, I mean, what's in here is a cubic, which means eventually, it's a positive cubic, so it's eventually going to make sure that there are domains where I'm not allowed to use negative values because I'll have to take the square root of a negative number. So I'm not allowed to use certain branches of this function, which is going to restrict which domains I'm allowed to use for my solution. Okay, so that's what this says. So even though our rectangle guaranteed that the rate function was continuous and its first derivative with respect to y was continuous for the entire real line, I'm really only guaranteed that a solution exists, well, for small intervals around my initial condition, and I would imagine it would look something like this. So this is where we distinguish linear and nonlinear equations. The nonlinear equations are much more difficult to solve, and it's a lot harder to tease information out of the rate function or from the differential equation to begin with. Right, so there was nothing in here that said that we should expect there to be some limitation on the independent variables solution domain. So this is very different from the linear equations, where, if you'll remember in the last video, we could figure out exactly the largest domain over which our solutions are defined, and it was specifically sitting inside of the equation. We could read it off of the equation. That's not the case over here. That is definitely not the case for nonlinear equations, and this is what makes them a lot harder to deal with in general. So let's see, did I have anything else I wanted to say? Yeah, one last thing then. Even if our equations were super nice, like the smoothest they could possibly be, y prime equals y squared, and we're going to give ourselves an initial condition of 1 at 0. And we can see, if I take this guy to be f, right, it's technically only a function of y, but it's y squared and partial f, partial y. I differentiate this guy to get a 2y. Both of these are polynomials. These guys are continuous everywhere. So my rectangle, AB cross gamma delta, right, the open rectangle where my function and its derivative are continuous, is actually all of R2. However, we can go ahead and solve this guy very quickly, and I believe we did at some point. Y of t in this case is going to be 1 over 1 minus t. Well, this guy is only defined on the interval from minus infinity up to 1, or from 1 to infinity. And the one that we take is the one that contains t0. Right? So in this case, t0 is 0, which means I have to take the interval from minus infinity to 1, which means that my differential equation actually blows up. My solution blows up in time, in a finite amount of time. So this domain is definitely not the entire real line, but I do have a solution that passes through y of 0 equals 1. But the problem is I can't read off what's going on. I can't see exactly what the solution looks like on this for this differential equation. In general, I can't see what it looks like, but I do know that there are some limitations potentially on its domain. So I think that's the last that I wanted to say here, apart from the fact that there's that general solutions don't necessarily take or that we might be missing some solutions when we use certain solution techniques. So just because you get a family of solutions using one solution technique doesn't mean you have found all of the solutions. All you've done is show that all these functions in here give you solutions with a given initial condition. It doesn't mean you found all of them. It just means that the ones you found are correct. Then you also have this problem with nonlinear equations where you can't solve explicit solutions. So the best you can get in general is an implicit solution, right? And that's fine. That's perfectly fine. But the problem is you're going to have to appeal to some other way of representing this function if you want to see what it looks like graphically, or if you want to analyze it any further. And this also gives us a good reason to start pursuing graphical and numerical constructions for these differential for these solutions of differential equations. And we'll see them a little bit. We'll talk a little bit about how you might go about constructing a numerical solution. And I think the biggest takeaway from this section, yes, is that nonlinear equations are much more subtle than linear equations. And there's one key corollary that I'd like to leave with at the end of this video. Is that no two solutions with, oh, let's see, how would I like to say that? No two distinct solutions can ever intersect. Right, two solutions to the same ODE can ever intersect. Right, because the reason being, right, the reason behind this guy, if you had two solutions that intersected, so here's a blue curve and here's a red curve, and they intersect right here, that would mean that there is a common intersection point, which means there's a common initial condition that these two solutions share. But the existence and uniqueness theorem, specifically the nonlinear version, says that I get a unique solution for every initial condition. And the fact is, because the red and the blue curves would be sharing such an intersection point, that intersection point constitutes an initial condition, which means that my solution would would no longer be unique. I'd have a red solution and I'd have a blue solution, and that violates existence and uniqueness. Therefore, I can't have solutions to the same ODE intersecting if they have the same initial condition. Cool, and that's where we're gonna leave this video. Let's see, at the end, yep. So that's where we'll go, where we'll stop for here, for right now. We'll talk a little bit more about existence and uniqueness in 2.8, section 2.8, in a little bit. But first, we're going to go ahead and start talking about specific cases of nonlinear equations that we actually can solve. But because of this restriction of there maybe not being an explicit solution, we're going to have to find some other way of analyzing these differential equations, and this is where we're going to go for the next video. We'll talk about autonomous